Long back, Businesq in 1885 actually gave a overview of this type of interaction where rigid footing is resting on a deformable soil mass, and then based on the settlement and the contact stress profiles were exhibited. So various types of contact stress profiles were given. Here only a typical one has been shown. The third one, we have interaction between deformable bodies, where both the bodies can deform, but they have to maintain mutual compatibility. Winkler in 1865, again long back, pioneered this work on beams on elastic foundations, where a foundation or a footing can be considered as a beam resting on the foundation soil, having uniform or varying subgrade modulus, and the beam is subjected to a uniform or varying load. It may be a point load, it may be a distributed load, or any combination, and we need to find out the deformation of this particular beam section. So these beams on elastic foundations is an example of interaction between deformable bodies. All these interactions finally lead to what we call as soil structure interaction problems. So when we talk about soil structure interaction problems, the most important thing what we come to during modeling involves various type of approaches. So we'll talk a little bit about modeling of SSI problems, where in general we have two classes: a discrete approach, or what is also called as a lumped parameter approach, and a continuum approach. In the discrete approach, we replace the soil using lumped spring or distributed springs. So we basically try to exemplify the soil through some mechanical elements and then exhibit the behavior. In continuum approach, we model the soil physically or numerically through some constitutive behavior, where we try to give or produce the stress, strain, and time characteristics of the soil. Now, discrete approach, since it uses mechanical elements, this is simplified and it is a computationally inexpensive approach. On the other hand, the continuum approach is detailed, and definitely as it demands, it may become computationally expensive. So which one to use, which one not to use, that depends upon a lot of different other issues. In the discrete approach, as I was mentioning, that we generally use the lumped or the distributed springs. So basically we use mechanical elements. Various types of mechanical elements are used to model the characteristics of the medium. It may be modeled through a spring, which represents the elastic characteristics of the medium. It may be modeled through a Saint-Venant element, which represents the limiting sliding characteristics of the medium. It may be modeled through a viscous dashpot, which represents the time lag deformation of the medium, and for soil that also can represent the dissipation of pore pressures. It can be modeled through a unidirectional bond, which tries to manifest the different responses in compression and tension as we have for soil. It may be modeled through a Zener element, which can represent the interlocking characteristics of various elements when embedded in the soil. These are some of the basic discrete elements, and then we club them together to form complex structures in order to represent the various complex behavior of the soil. On the other hand, in continuum approach, we do not reside to these discrete elements. Rather, we provide or we deduce the stress strain time characteristics, or what is called as the constitutive relationship. So we have linear elastic relationship, as we understand through Hooke's law, where stress is proportional to strain. We may have nonlinear elastic relationship. We may have elastoplastic relationship. We may have different types of plasticity, including yield pseudoplastic, Bingham plasticity, or yield dilatant. And then combining all these simplified relationships, we can have much more complex stress strain time characteristics represented through this continuum approach. So these are the two distinct classes of modeling of SSI problem, and we will look into a bit of these two as well. Coming to the part of seismic soil structure interaction. So till now we were talking about soil structure interaction. As the name suggests, the soil structure and the interacting part, the substructure on the foundation, interacts with each other. When we use the word seismic, immediately we try to assert that we have seismic waves traveling through the medium. So in the left hand side figure, you can see a fault plane which has ruptured, and due to this rupture, stress energy waves has generated from the focal point, and it may travel directly upwards to the free ground where there is no structure present, or it may travel through the soil medium to the places where structures are existing. So in this seismic soil structure interaction, we have to understand various factors which affect the seismic soil structure interaction and subsequent response. One of the most important characteristic we have is the travel path effect. When the fault rupture takes place, it does not rupture at one point, rather a rupture takes place along a direction. Now whether your structure or your important entity is present in the direction of fault rupture, or whether it is present away from the direction of fault rupture, that governs what type of waves or how the waves will get propagated to the structure. Those features are represented. These fault ruptures generally take place in the rock bed, as you can see in the right side figure, and the waves travel through the rock bed and then it reaches the overlying soil. Now this soil, being of lesser stiffness than the rock, creates a change in the wave characteristic. Depending on the soil properties, it may amplify, it may attenuate, or it may change the entire frequency response of the incoming waves. Now as I mentioned earlier, when these waves reach the free ground surface where there is no structures existing, what we record or what we obtain is a free field response. Many times it is represented as double F response as well. Whenever there is a structure, now the structure gets affected by the incoming waves. It starts to vibrate, it creates its own response and passes some of its response again back to the soil. So whenever the structure is present on the ground surface, we start getting the problem of SSI or soil structure interaction. In this particular case, since the seismic waves are involved, we will call this problem as seismic soil structure interaction. Now SSI interaction response is different from the free field response. In this part, we will briefly talk about kinematic and inertial interaction, which forms the crux of this SSI analysis. Let us look into the picture of a structure embedded in a rocky bed. So we have a rigid rock bed in which the structure is embedded with the aid of its foundation. Since the rock bed is rigid, the motion at these points A and B shown in the side of the structure, they are more or less the same. The rock bed has very high value of elasticity. It does not attenuate or it does not amplify the incoming wave. More or less in practical, the response at A and B are always the same. Since this response is same, there is no deformation at the base due to the shear or overturning moments. That means whatever input motion you can give at B, the same motion will be reflected at A. There will be no shear or overturning moments generated at the embedded base, and hence there will be no deformation in this particular condition. So in this type of system, instead of applying the motion below the rock bed, you can directly apply the motion at the base of the foundation. And this forms a very important part of the analysis in soil structure interaction, which is very, very commonly done, which is called as the fixed base analysis. On the other hand, let us now consider a structure which is embedded in a soil overlying a rocky bed. The soil is much more flexible than the rock bed, or in other words, the stiffness of the soil is comparatively lesser than the stiffness of the rock underneath the soil stratum. In this particular condition, let us first assume that we do not have any structure. So we have the rock bed over which the input motion is incumbent. This input motion travels from this rock bed to the top of the soil at the ground surface. The soil being flexible, it changes the characteristics of the motion, and whatever response we get at the ground surface is called as the free field response, or in other words, it is the motion in absence of any structure. However, the soil being flexible, it changes the characteristics of the motion which was there at the rock soil interface. Amplification takes place in most of the cases. In some cases, attenuation is also observed. Whether amplification or attenuation, that will be mostly governed by the frequency content of the propagating soil medium. So in such cases, in the free field response, the behavior of the soil without any structure is reflected. Now let us embed a condition where we are considering the structure but considering it to be a massless. So we have a rigid base of the structure and the structure does not contain any mass. So we consider only the stiffness of the rigid body. Now, unlike what we have seen a rigid rocky bed, a rigid body resting in a flexible soil medium will undergo rigid body, horizontal and rocking motions. So this type of interaction where you consider a rigid body embedded in a flexible medium where the rigid body is massless and only the stiffness is considered, that is called as kinematic interaction. Once we get the response of this kinematic interaction, next if we consider the mass of the system, so we know the accelerations, we know the mass of the system, so mass times accelerations help to develop the inertial forces, and due to these inertial forces in the structure, now the base foundation of the structure experiences overturning moment and shear forces. These overturning moments and shear forces are further responsible to change the free field ground motion which we originally used to understand the soil response. So this type of interaction where inertial forces change the ground motion characteristics, those we call as inertial interaction. This kinematic and inertial interaction together forms the basis of what we call as soil structure interaction analysis. Now, many a times a question is brought up. Do we have evidence of SSSI? Do we have evidence of seismic soil structure interaction? From when did we start? So it all started from the Kobe 1995 earthquake, when there was a huge 18-segment collapse of the Hanshin Expressway. Another figure to show the collapse, you can see that it has just overturned. The pile supports did not help to protect or did not help to prevent the overturning, and then lots and lots of analysis has been done as why such occurrences have taken place. Milonakis and others in 2000 published a paper where they have actually brought out the influence of SSI analysis in obtaining the response of this particular system. If you see, when SSI was ignored, the acceleration or the peak acceleration response at the top of the structure was obtained to be 1.07 g, which was originally used in the design. However, when SSI was incorporated into the analysis, at the same point, you can see now the maximum acceleration comes out to be 1.36 g, which is nearly 25% increase. Such increase in acceleration will induce huge amount of inertial forces on the cantilever portion of the standing structure, and that will result in huge amount of deformation or rocking or translation at the base, which is basically considered as a reason for this hunching failure. So flexibility of this foundation, which is incorporated through the SSI analysis, imparted more acceleration in the superstructure and is a probable explanation for the failure of this hunching earthquake. So this is the one incident from where it all started, and huge amount of research has been done after this particular incident has been taken as the evidence of seismic soil structure interaction. When we look into the solution, so we have to analyze the SSI problem. Again, there will be various different types of analysis approaches. We will just have an overview of that. The first type is called a single step method. So we do the entire analysis in one step. So what do? We consider a structure embedded in a soil domain, and we apply the free field response all along the boundaries of the domain. So UFF is the free field response applied to the model boundaries, and then we simply solve the equation of motion in finite element domain. So we have the mass of the system M, we have the stiffness of the system K, and we try to find out the deformation or displacement at any point as U based on whatever acceleration response is applied at the boundaries. This method is capable of conducting nonlinear analysis. However, there are apprehensions that in this case the damping matrix is not well dealt. You can see that the damping is not really taken into consideration directly. There are indirect inclusions, and in order to solve this problem in general, a large size model domain is required. The second approach, which is more common, is a multi-step method, where first the kinematic interaction is looked into. Remembering our previous discussion, in the kinematic interaction we have the soil domain, we have the structure which is massless, and we use the base deformation at the bottommost boundary of this domain and try to find out the relative displacement at the degrees of freedoms. That means at all these interface between the structure and the soil, we try to find out what is the relative displacement UKI. This relative displacement is also referred to as the foundation input motion, or FIM. So through this kinematic interaction, we started with a basal input motion, and we moved into the foundation of the structure and obtained the foundation input motion. As we discussed earlier, in the inertial interaction, we will use this foundation input motion at the base of the structure. We will include the mass of the system. Due to this foundation input motion and the mass of the system, we will have these inertial forces generated and applied to the structure and foundation. Just to remember, in this particular analysis, the foundation or the model domain foundation should not move anymore. So all these lateral and vertical boundaries, lateral and horizontal boundaries of the model domain remain fixed. So in this case, what we do, we apply UKI, which we obtain from kinematic interaction, plus whatever basal displacement time deformation we have. We try to find out UII, that is the displacement due to inertial interactions. There is one more method, which is the substructure method, a three-step procedure, which is more or less similar to the multi-step method. So in the substructure method, again, first of all, you determine the free field response of the site. Using the free field response, you try to find out the foundation input motion, that is a part of the kinematic interaction. Again, using this foundation input motion, you conduct the inertial interaction analysis. However, in this particular method, when you conduct the inertial interaction analysis, you replace the soil with lumped elements whose coefficients are basically obtained from impedance functions. We will not go into the detail of that. I'm pretty sure many other speakers will be talking about that. So in the earlier method, in the multi-step method, we did the entire analysis by considering the soil domain to exist. However, in the substructure method, in the third step, we removed the soil domain with the help of lumped elements. Apart from this, there are many other popular and commonly used continuum-based methods, the finite element method, the boundary element method, the scaled boundary finite element method. I am aware that Professor Maheshwari yesterday had talked about little bit about the scale boundary finite element method. Other methods will be again talked about by other speakers in much detail. Here we will concentrate on the overview of the numerical modeling. So the most important thing which comes into the aspect of soil structure interaction analysis is the modeling of the soil domain. How do you do the modeling of the soil domain so that proper response is obtained? Two different approaches are commonly used, the simplified modeling approach and the detailed modeling approach. We will first look into the simplified modeling approach, where in this type of approach, mostly the lumped parameter models are taken into resort. So we may have a lumped spring model where you can see we have a shallow footing which rests on the foundation soil, and this shallow footing have 6 degrees of freedom, 3 translational x, y and z, and 3 rotational along the x and y and z directions. What we do in this lumped spring model is that we concentrate the entire soil mass and their stiffness and form the lumped elements concentrated at one particular node. So we will have a spring element related to vertical stiffness along y, lateral stiffness along z, lateral stiffness along x. Similarly, we will have rotational spring elements to take care of the torsional stiffness about y, rocking stiffness about x, and rocking stiffness about z. Again, the properties, coefficients of these mechanical elements will be obtained from the impedance functions as discussed earlier. So we will have equivalent springs for different degrees of freedom. Now in this particular case, we are concentrating everything to a particular point representing a node. A better model is a distributed spring model where the foundation rests on a set of discrete springs, and when this foundation is loaded, the set of springs beneath the foundation gets deformed. Soil pressure P at any point is related to the vertical deflection Y. So whatever deflection is encountered by the spring, and the subgrade modulus K. So I am aware that Professor Kaushik Dev yesterday has talked about the subgrade modulus through the plate load test, and many examples were given. So in this case, soil pressure P is related to the vertical deformation Y as P equal to Ky. Instead of simply using spring which only reflects the elastic characteristic, we can have an elastoplastic model. Again, a Saint-Venant unit will be used where a spring will be encompassed with a plastic element. So we have the elastic characteristics through spring, plastic characteristics through the Saint-Venant element. The advantage is that in this particular model, we can make a transition from elastic strain to plastic strain and can apply the yield criteria as well. For the details of this, you can see in the research paper mentioned. When coming to pile foundations, one of the very popular method of modeling the soil domain and the soil structure interaction is through beams on nonlinear Winkler foundation or BNWF model. You can see in this particular figure, the pile is represented by this curvilinear portion. The pile supports a superstructure. We have a free field soil column response, and the free field soil column response has a transition to the pile soil response through this particular set of mechanical elements, which are basically nonlinear TY springs and dashboards. So in this beams on nonlinear Winkler foundation, the pile is basically considered as a beam which is rested or which is supported by a set of discrete nonlinear py springs and dashpots. So whenever we try to find out the soil pile interaction force, whatever is the displacement of the pile shaft at a particular point, that will be used to find out the force or the stresses generated at the same particular point, which basically follows the Winkler's hypothesis. At one particular point, whatever is the response, that remains independent of the response of the other particular points. So we have independent of the interaction effect above or below the stated point, that again being a part of the Winkler's hypothesis. The hypothesis has been modified over the time, where we have actually established that pile can be acting as a beam, which itself can provide a connection between the deformation of these set of springs throughout the length of the pipe. So as I was mentioning, pile is generally modeled as the beam column element, and over that the stick model of the structure is provided. The discrete elements represents the soil contribution. So these discrete elements are made up of nonlinear springs, which can be represented through their Py or Tz curves, and we have viscous dampers. So what are they used for? These set of nonlinear springs and viscous dampers and their combination is basically used to represent the near field and the far field effect. The near field effect, in simple terms, is basically how the soil near the pile is getting influenced, and the far field effect, again in simple terms, how the soil away from the pile is getting influenced. The far field effect mostly comprise of the free field response, and the near field effect mostly comprise either the transitional or the soil structure interaction response. Moreover, these set of discrete systems also help in modeling the radiation damping and the material or hysteretic damping. To look into the hysteretic damping and radiation damping a little bit. So the material or hysteretic damping is basically a manifestation of the cyclic loading of a sample. If we have a particular soil element and we shear the soil element continuously back and forth, there will be dissipation of energy. So in this process, we represent a soil element by a Kelvin void body. It is a simple parallel system of a stiffener and a viscous dashpot, and they are sheared in a cyclic manner. Once this shearing is done, there will be a cycle of loading and unloading followed by a reloading, and we obtain a loop which is called as a hysteresis loop. So this is a plot of shear stress versus shear strain, or shear force versus shear displacement, and the loop which we get is called a hysteresis loop. The area within this loop actually provides the energy dissipated per cycle, and the area bounded by this shaded triangle provides the peak energy during that particular cycle. Based on this expression, based basically on the ratio of energy dissipated to the peak energy, we can find out the damping ratio. So this comprises the material or hysteretic damping characteristics. Next, we have radiation damping. As the name suggests, the waves move on, and the influence of the waves get redundant as they move far and far away from the point of generation. So in terms of one-dimensional wave propagation in an infinitely long medium, it should not happen that the waves get trapped or reflected back into the medium. So a wave which is moving away from the medium to the boundaries should not come back again in the system when we numerically represent them or when we do a numerical modeling. So we generally provide a viscous dashpot at the boundaries, which basically act as an absorber, and then by this way we tackle the radiation damping. So whatever viscous dashpot you will be using, you have to give a viscous dashpot coefficient, which depends upon the mass density of the propagating medium. A is the area of influence through which the wave is passing through, and V is the velocity of the propagating medium. So based on these particular terms, you can decide what should be the value of this dashpot coefficient so that the radiation damping can be ensured in the numerical modeling. Now, in order to model this soil damping in BNWF approach, there are two specific ways by which we do this modeling. One is called a parallel damping model. So on the left hand side, so this is the beam column element representing the pile. This is the beam column stick element representing the superstructure. And you can see at the various pile nodes, it is connected to a complex mechanical element which has a elastic spring and a Saint Venant in parallel, which is further attached to a spring in series, and then the entire system is attached to a viscous dashpot in parallel. So this is basically called as a parallel damping, where this entire complex mechanical system provides you nonlinear PY spring and radiation damping dashpot, and the far part represents the free field motion which is incumbent on the pile. The other way of doing is a series damping. So where a Saint Venant element and a spring element is in series with a spring element and a viscoelastic element. So in this case, the first element is considered as the near field element, which helps in tackling the strain hardening plastic or the hysteretic damping or the material damping. And the far field element helps in tackling the radiation damping. It is the viscoelastic element. If you see in comparison, in the parallel damping, the near field and far field effects are clubbed together, whereas in series damping, the near field element and far field element are completely separated. The second one, that is the series damping, is considered as a better and appropriate model in between these two. There are far more advanced models where there is a near field element, there is a far field element, and there is a transition element present as well, which converts the near field composition to a far field composition. We also need to model the PY curves for finding out the pile response. Now these PY curves mostly comprise of both elastic and plastic components. So if this is the PY curve for the pile response, so it is the stress deformation response. We have an elastic part, we have a plastic part as well. Now there are different ways of determining these PY curves or TZ curves, as I mentioned earlier. It can be done through experiments, it can be done through numerical modeling, it can be done through any other types of techniques which are commonly available through analytical measures. This BNWF model is very popular when we come to the simplified modeling approach of pile-soil interaction. This model is quite versatile and it is considered as the most efficient model among the simplified methods, which has lesser computational expense. So it is computationally efficient. The results which you get from the BNWF model are in quite accordance with the finite element or finite difference models, which are more and more rigorous. However, BNWF model is actually simpler than the FEM or FDM model. This particular BNWF model has several advantages over other simplified methods that we could realize from the previous 4 or 5 presentation slides, and many complex conditions can be modeled. Having said all these advantages, we should always remember that finally it is a lumped parameter model. The inherent deficiencies of lumped parameter model, that the mass, stiffness, deformation, or any other response are lumped at particular nodes in the system, that inherent disadvantage will always be prevalent in such models. Next, we will look into the modeling of soil domain through a detailed modeling approach, where we take help of continuum mechanics, constitutive models, where we try to represent the entire semi-infinite, linear, elastic, homogeneous isotropic solid, that is our soil medium, in the context of earthquake wave propagation and in a finite element basis. As mentioned earlier, instead of finite element, you can go for boundary element or scaled boundary finite element or any other advanced methods. One of the most important part in this continuum approach, in this detailed modeling approach, is to decide about the extent of soil domain. So I may have a structure as is shown in this figure. I need to decide what would be the extent of the soil domain which I need to use in modeling. How much will be the vertical extent? How much will be the horizontal extent? In case of static modeling, we already know that we have these pressure bulb conditions which we can take help of to decide the horizontal and vertical boundaries. But in this particular case, where the seismic waves are inflicted on the soil foundation structure system, the pressure bulb approach cannot be used. So one way to find out is to do trial and error, and that may take ages to find out. So there are certain specific guidelines which are available in order to start your modeling. The vertical extent in general is taken entirely up to the rocky stratum if available, or a sufficiently rigid stratum. Rocky or rigid stratum here signifies that particular stratum which does not contribute to soil amplification, or which does not contribute to the amplification of the wave. So any medium, any depth of medium which has potential of contributing to the wave attenuation or amplification needs to be modeled. What about the horizontal extent? In the horizontal extent, we follow two approaches. One approach is that, as we already mentioned, that when the waves reach the ground surface, we obtain a free field response. When the waves reach the regions near the structure, we obtain a response from SSI. So we need to fix that horizontal length of the domain where free field response is actually obtained. So any response what is obtained within that extent will have some influence of the structural response. So SSI response, extent of SSI response should be averted and free field response should be obtained, and that gives us the first guideline of the extent or horizontal extent of the soil domain. So in the horizontal extent, we should find out the distance from the structure foundation system beyond which free vibration response of soil is attained. Now the question is, how do we know that whether the response at this point is a free response of the soil? So we have this analytical expression that if you have the height of the soil as h, if you know the shear wave velocity of this particular propagating medium, you can always find out the time period for the free field response. In your numerical modeling, find out what is the distance beyond which you are getting the time period equal or very similar to this particular value, and then you can decide upon your horizontal extent. At the same time, even after doing that, these boundaries sometimes play a crucial role. As we mentioned, that these boundaries should not have any waves getting reflected back, or basically we say these boundaries should not have influence on the response of the structure or the foundation. So the lateral extent should be so placed that the boundary effects are negligible. So the response of this structure soil foundation system should not be affected by boundary reflection. So based on these two, we decide for the horizontal extent. The next important part remains discretization in finite element and meshing. Now a question comes, what would be the size of mesh that we should adopt for such numerical modeling? The basic context is that whatever be the size of the mesh, it should be able to capture the characteristics of the smallest wavelength passing through this particular system. Now, when we talk about seismic waves, it is basically a wave front, or it is a packet of waves where various waves of different frequencies and wavelengths will be traveling through. So Lismer and Kuhlmeier suggest that the maximum size of finite element should be 1/8 to 1/10 of the shortest wavelength. The shortest wavelength is again related to the wave of maximum frequency passing through this medium. So maximum size of the finite element mesh should be in relation to the maximum frequency of the wave passing through this medium or maximum frequency content of the seismic wave used as input. The next important part which comes in continuum approach is interface modeling. So you have the pile soil interface, you have the footing soil interface. Interface modeling plays a big role because this interface is the part of the entire system which transfers the load from pile to soil or soil to pile. These interfaces are basically the contacts of the soils and foundations, and they experience large degree of nonlinearity of various forms. They may have huge amount of sliding, considerable degree of separation, even undergo uplift. For example, let us take this figure, which is basically a well foundation rotating about its pivot point within the soil, and there is a water layer above it. So if we recall our earth pressure systems, if any structure moves away from the supporting soil, it is in active state. If a structure moves towards the supporting soil, it is in a passive state. So if we consider this pivot point, the right hand side of the well below the pivot point is moving away from the soil, and on the right hand side we get the active pressure zone. Similarly, on the left hand side above the pivot point we get another active pressure zone. Whenever we get this active pressure zone, if the soil is of such characteristics, then there may be a separation in these active pressure zones. On the other hand, the right side of the well, which is above the pivot point, is undergoing a compression and exhibits a passive pressure zone. Similarly, the left hand side of the well foundation below the pivot point exerts a passive pressure zone. Now, since this is in compression, the soil also tries to move away. So these passive pressure zones are more subjected to sliding phenomenon. And the more we come towards the lesser confined parts towards the top, we may have the uplift characteristic. So all these behaviors needs to be modeled through the interface modeling or through the contact elements. Otherwise, we will be basically losing lot of information about the stress transfers. A very common way of doing that is a zero length frictional contact element. Now, whenever you use a contact element, you have to define its stiffness appropriately. In this particular case, you have to define the stiffness both along the shear, that is the tangential direction, and along the normal, that is towards the direction of the deformation or towards the direction of the load. There are thousands and thousands of types of contact elements, and they have their own characteristic conditions and definitions of providing the shear and the normal stress characteristics. Chang et al. 2000 tried to look into what difference does it create by considering interface nonlinearity in soil structure interaction problem. So in their research, they found that the stresses were reduced by around 40% when interface nonlinearity were considered. The other way what was done is that there is no interface nonlinearity, it is in full contact, and in that way much higher stresses were generated. So that means interface nonlinearity provides a good amount of difference in the modeling and in the subsequent results, which we must not ignore if we want to approach the practical realistic conditions. Coming to the modeling of pile soil interface, again on the right hand side of the figure you can see that there is a pile. Remembering that pile is made up of a beam column element. The shaded area is the soil. Remembering that soil is made up of 4-noded quadrilateral element, and in between there are some hollow circles which represent some dummy nodes. The interface modeling, the crux or the context of the interface modeling remains the same as earlier. However, there is a bit of problem here. The structure or the pile node, these are called as the master nodes in this case, they are made up of 3 degrees of freedoms, whereas the soil nodes, they are made up of 2 degrees of freedom. Now this 3 degree of freedom and the 2 degree of freedom system cannot directly interact with each other. There will be a incompatibility in the response, and that's why a dummy node is introduced. So these dummy nodes are given as these hollow circles. So what are these dummy nodes? These are constraint nodes of 2 degree of freedom at each node. These are called as the slave node, with a special implementation of equal displacement as that of the pile. So this dummy node serves as the transition of response from the pile node to the soil node and vice versa. To see the dummy node in a single element, so the dummy node is connected with the soil node with a zero length contact element as was shown in the previous slide, and the response of the dummy node is exactly equal to the pile node, which is ensured by equal DOF constraint. So this dummy node is extremely important in this pile soil interface modeling when two different systems of different degrees of freedoms are interacting with each other. The next most important thing which has to be considered in any numerical modeling based on continuum approach or detailed modeling approach are the boundary conditions. Now, as we started this discussion of continuum approach, that we want to model the soil as a semi-infinite domain, but it is actually impractical to model. You need innumerable number of elements which will generate immense computational expense, and we really need to curtail this entire soil domain with proper boundary condition. So the boundary conditions are such that whatever finite domain we choose is basically a representative of the semi-infinite domain with some tolerance. We may have different type of boundaries. The initial or the most common one is the reflecting boundaries. This figure I have shown earlier. So in the reflecting boundary, we have zero displacement condition at the bottom, so which is basically fixed from deformation in any direction. On the lateral boundaries, we have the zero stress boundaries or the roller boundaries, which can deform only vertically. However, the problem with the reflecting boundaries is that whatever waves reach towards the boundaries are reflected back into the system. So the waves get trapped, they start interacting with each other, and they create a box effect or basin effect where there will be standing or stationary waves. And this results in spurious oscillations when we find out the response of the system. So what to do? What is the way out? We create a non-reflecting boundary, or which is called an absorbing boundary. So the target of these absorbing boundaries is that whatever P waves or the S waves, whichever reaches the boundary, should not get reflected back and should be completely absorbed. As was already told in one of the previous slides, that we use viscous dashpots in these particular boundaries to absorb the incoming waves. Again, depending upon the orientation of the dashpot, we check whether it looks into the S wave characteristic or whether into the P wave characteristic. paper so inherently assume that all the waves here is not the waves by the boundary, which it has. So we can we need to be from this. So we have the detailed modeling, and I mentioned the detail that three important aspects of present and domain is modeling and it starts at the crux of the mechanism of so which we find out the length of the simple and complicated cases we have to deal in real life. Those parameters are short and to and it's a huge computational and time expense. So we looked into a problem which we brought upon. One student, Dr. has brought upon this problem. We tried to give a proposition for the optimum lateral domain. So the modeling basically involves RC frame on Python. And we Apple wanted to go for implicit. This is a figure of a RC frame supported by pile foundation. Whatever you see in here, pile video, pile group, and structural configuration length of the domain. For all these figures, you can see that these figures have an initial sharp drop in RMSE, which is mostly in the smaller values of normalized domain lengths, and then they have a much lesser slope in some cases as in total. This means that when the domain length is smaller, that means boundaries are near to the structure, any change in domain length or any change in the shift in the boundary would change the response to a significant amount. Beyond certain point, the change would be marginal or even there might be no change at all. So our target was that for each combination, we need to find out that domain length, which we will be calling as optimum domain length, which can be used for the numerical modeling. So what we did, this is a representative plot. So we have normalized RMSE, we have the normalized domain length. These small dots are obtained from those numerical exercises. We fit a bilinear plot, and wherever this bilinear plot intersected with each other, we get the optimum point. So this optimum point indicates that domain length beyond which there will be marginal change in response. So we collected these optimal points for various combinations. So for various combinations of earthquake, soil, structural width, we did this exercise and found out these optimal points for each of the combination. We clubbed them all together because giving this is of no use. We clubbed them all together to find out how the optimum domain length changes with the PG. Just going back to the previous picture once more, based on all these exercises, what we understood that structural width and PGA are the most important parameters which was governing the optimal domain location. So this optimal domain length was plotted against PGA for various types of soil, and again a best fit linear plot is provided. So what we did is that we gave a proposition depending upon PGA how the optimum domain length should change. So we provided variation of optimum normalized domain length with the PGA. We clubbed all this together to finally give a very robust and novel proposition for optimal domain length to be selected for numerical modeling for various structural widths, which depend upon various magnitudes of PGA being considered. So let us say if you are analyzing for a structural width of 25 meter, you have a PGA value of 0.22 G. You simply select an optimal domain length in the numerical domain, which is 5.5 times 25. If your PGA is 0.43 G, you choose this particular value around 6.6, and similarly in the other cases. Any PGA between 0.22 to 0.82 can be successively interpolated in this region. I would caution that since we have not checked below 0.22 G and above 0.82 G, we would issue a cautionary statement that don't extrapolate. It is always better to extend this research further and bring in new understanding. Much more work has been done in this domain. For further readings and details, you all can visit these reference papers which was published by Nishant from his PhD thesis work. Some are still in the process of publication. All these are available in my website and ResearchGate profile. All the details which are not mentioned here, intricate issues, everything you can find in these papers. So coming to my final remarks, we were discussing about the modeling of the seismic soil structure interaction problem. We talked about a little bit about the lumped parameter and the continuum models in lieu of their kinematic and inertial interactions. We looked into few overview of the analysis approaches, the single step, multi-step, substructure and other analysis approaches. We talked about the simplified modeling of soil domain through lumped approach, where we shown lump spring, distributed spring, elastoplastic model, BNWF, importantly for the pile soil interaction modeling, and we have shown a little bit about the modeling of damping and PY curves. We also talked a little bit about the detailed modeling of the soil domain through a continuum-based approach, where we mentioned the three most important aspects: extent of soil domain, interface modeling, and boundary conditions. And based on this understanding, I presented to you a small work done from our side about dynamic SSI analysis of RC frame buildings on pile foundation, where we proposed a new method of giving optimum lateral extent of soil domain for SSSI problem involving the RC frames. Now, having said this, a question always lurks. You will find this question everywhere, everybody asking, SSI, whether its consideration is detrimental or beneficiary. You will find two big groups fighting all over the world among each other. Some says it is detrimental, we should not consider. Some says it's beneficiary, we should not consider. We should move a little bit away from that. Let us not try to fight over the fact whether SSI is detrimental or beneficiary. Rather, let us try to incorporate SSI so that we can decipher important realistic response of soil structure foundation system under the dynamic conditions. If through that analysis it is found that the response is not significant, it's well and good. Otherwise, we are always on the practical, realistic side. At the end of my talk, I would like to provide an acknowledgement to the organizers of this conference for this faculty development program, to the Department of Civil Engineering, GBP, IIT, to provide this platform to discuss about various interesting issues of SSI. Various speakers will be talking about various different things, and I am pretty sure that collating all these talks and lectures and interactions would provide a good treatise for any of us to start with the SSI solutions and background. I would appreciate all my students, with special appreciation to Dr. Nishant. All of them have been the workforce in bringing out all these intricate findings over years. So Nishant has been working on this particular problem over the past 7 years, and we are happy that he has come out with very good findings. My sincere appreciation to Professor Kaustubh Dasgupta. He is my collaborator from the Structural Engineering Division, IIT Guwahati. He is like the structural pillar of our SSI group, and we have been working together with lot of students from long time over various issues, and over the coming years we are hopeful to bring up further new interesting ideas as well. And finally, to all those researchers whom I was mentioning or whom I have not mentioned in these previous slides, whose works have helped us to progress and discuss today what we are talking about, the SSI analysis and interactions. So that will be all from my side. Thank you very much to all of you for the patient hearing. This is distressing time, but still within this distressing time, it is good to share and interact with each other so that the knowledge transfer does not get limited. My website and ResearchGate profiles are given here. All the papers, all the documents are freely available from there. You can freely download. If you cannot, drop me a mail. We can send you a copy of whatever you require. So that will be all from my side. Thank you. I'll be handing over to the organizers and the moderator for further proceeding. Thank you all.